and welcome to this video on photons, energy quantization, and the photoelectric effect. In this session, we will explore how light behaves at the quantum level and why energy is carried in discrete packets called photons. We will introduce the Planck-Einstein relationship, examine the photoelectric effect, and understand how photon energy depends on wavelengths. Finally, we will connect this concept to semiconductor, bandgaps, and solar energy conversion, providing the physical foundation of modern photovoltaic devices. End of 19th century, physicists face a major problem known as the ultraviolet catastrophe. Look at this red dashed curve, which shows the prediction of classical physics using the Rayleigh-Jeans law. As the wavelength increases and also on the other hand becomes shorter, you can see here that the wavelengths become shorter, the predicted energy increases without limit. This is the Rayleigh-Jeans law. According to this model, a hot object should emit an infinite amount of energy at very short wavelength, which clearly does not happen in reality. On the other hand, the blue curve shows the experimental behavior correctly described by Planck's law. Instead of increasing indefinitely as it was from the Rayleigh-Jeans law, the spectrum reaches a maximum and then decreases. To solve this, Planck proposed that energy is not emitted continuously. Instead, the energy is emitted in discrete packets or quanta. This simple idea became one of the foundations of quantum physics and eventually led to our modern understanding of photons and light matter interactions. Now that we have introduced the idea of quantized energy, let's look at the relationship between photon energy and the wavelength. E equals h nu, or E equals h nu equals hc over lambda, in which h is the Planck's constant, c is the speed of the light, and the lambda is the wavelength. These equations tell us that photon energy is inversely proportional to the wavelength. Look at this, the spectrum of the light. You can notice that the ultraviolet or UV photons have the highest energies. Visible photons have intermediate energies, and infrared photons have the lowest energies. For solar cell calculations, we often use the simplified relation, which is E in electron volts is 1240 over lambda in nanometer. This allows us to quickly convert wavelength into photon energy. This relationship is fundamental because semiconductor absorption depends directly on photon energy rather than wavelength itself. Now let's look at the Einstein's explanation of the photoelectric effect. A single photon transfers its energy to a single electron, for example, this electron. If If the photon energy is greater than the work function of the materials, the electron can escape from the surface. The work function, shown by phi, is the minimum energy required to remove an electron from a material. If the photon has the energy enough to remove this electron from the material, photoelectrons are emitted immediately. Einstein summarized this process with K maximum, which is maximum kinetic energy of electron, equals to h nu, which is photon energy, minus work function of the material, phi. The photon energy is first used to overcome the work function, and any remaining energy becomes the kinetic energy of the emitted electron. An important result is that increasing light intensity produces more electrons, but increasing frequency produces more energetic electrons. This discovery provided a strong evidence that light behaves as discrete particles called photons. Let's conclude this video by connecting photon energy to solar cell absorption. Every semiconductor has a characteristic band gap energy, which is Eg, which defines the minimum photon energy required for absorption. Look at here. The corresponding threshold wavelength is given by Eg equals hc over lambda g. Photons with energy below the band gap h nu, which is smaller than Eg, cannot excite electrons across the band gap. As a result, these photons pass through the material without being absorbed. These are creating the transmission losses. Now here we have the photons which have h nu greater than Eg. Photons with energy above the band gap are absorbed successfully. However, any excess energy above Eg is lost as heat through a process called thermalization. This means that both low energy and very high energy photons contribute to efficiency losses. So now it is clear that the challenge in photovoltaic design is therefore to select a bandgap that captures the largest useful portion of the solar spectrum while minimizing these losses. Now we can conclude this video. Let's be in touch and wait for the update about our new videos and concepts. Thanks for watching.